Well, hello everybody. Welcome back. All right, so we're getting back into things. Hold on, I'm trying to position my mic in a way that's not super loud. I don't know what's going on right now. Needs to be a little louder than usual. If I turn this knob, maybe. I think that's better. Okay. Anyways, let me do some positioning here so that I can actually get my mouse a bit better. All right. So where we left off, we're gonna be continuing on with. Hold on a second. Hello, I forgot to turn my light on. But bam, hello. That's my button. My bad. There's a button on my shirt. I thought I had something on me. Alright, so what we're doing is we're gonna be learning about state machines. So we'll see how this goes. Is this anything worth? Well, I'm sure it's plenty worth worrying about, but I don't know much about it. So turn this down.
Honestly believe that this is one of the first things that you should learn as a Godot beginner once you've mastered the basics of the engine. Alrighty, it's another devlog with some progress on my game so far and also some tips for my fellow Godinsky developers. It has been a few weeks since I've last showed you the progress on my 2.5D platformer featuring this little fella.
Fuck yeah.
We have moved from a very basic prototype with simple shapes and a moving camera to a setup that lets me add a 2D background, a middle background, and 3D objects and sprites in the main area of the game. And while my character could run and jump, I still needed to figure out how to make the combat work. So that's what I set out to tackle next. I had already envisioned the move set. It was a mix between Super Smash Bros. And the classic beat-em-up games. With the weekend ahead, I knew what I had to do. Create my first combat system with my minimal programming skills. After a long day of work, I had something functional. But every time when I tried to add a new move, two others would break. I ended up with massive functions in one code file to handle all movement on the ground, in the air, while moving, while standing still, and don't even get me started on managing the actual sprite animations. If your logic code is starting to look like a tangled mess of spaghetti code, where you are checking multiple states just to add another if statement inside, then something's wrong. Yeah. And some would say that if it works, it doesn't matter, but yeah, that only goes to a certain extent. At some point, you cannot add more logic to an already mess of a code. Let's just put it like that I didn't have a good day. I was so annoyed. I literally had nightmares that night, and I'm not sure if you guys ever had them, but I was stuck in some sort of if statement loop in my nightmare, and it had to do with like real life situations. It was like a living hell. So the next day, I realized that I couldn't rely on the monkey brain alone, and I did some research on how smart people
just put my streams over here.
Game character states. And that's when I discovered state machines. When you are creating a game, especially a platformer, your character will likely have different states, like running, jumping, or attacking. When your character is running, it is allowed to jump, and when it's jumping, it can only fall, for example. You could manage all of this with a bunch of if statements, checking what state the character is in or is not in, and then run the specific code. But as your game grows, this can get really messy and hard to keep track of. This is where a state machine comes in handy. Instead of cramming everything into a big script, a state machine lets you break things down into separate, clear scripts for each state. So when your character is running, only the code related to running is active. When the character switches to jumping, the game automatically swaps out the running code for the jumping code. This approach keeps your scripts much more organized and easier to understand because each script only deals with the functions and behaviors that are specific to that particular state. It makes your code cleaner, but more importantly, it also makes it more maintainable. You can easily add different logic along the way as your game grows. I honestly believe that this is one of the first things that you should learn as a Godot beginner
Okay.
once you've mastered the basics of the engine. Learning the fundamentals of object-oriented programming, where specific code can independently function in its own state without interfering with the rest, is a game changer. Once you grasp this concept, it will influence everything you program from that point onward. I'll be sharing a few helpful videos in the pinned comment and the description of this video that you should check out next. And
Sick.
while this video isn't necessarily a tutorial video, I will show you how I roughly implemented the state machine to make the combat work. Alright, let's just go straight to the debug mode of the current build. I also just upgraded to the newest version of Godot, and surprisingly enough, most of the things didn't break down. Only the water mesh I had to fix. I'm not completely sure what you guys on YouTube saw last time, because I'm also regularly showing things on Discord. If you want to join, the link is also in the description of this video. But this is the current build. Let me just go ahead and kill a bunch of crabs.
Oh yeah.
Yeah, so that's basically it. That's the video. Thank you for watching.
Nice. Thanks.
No, I can talk about a few things, to be honest. I think in the last build I already had the movement working, but since I found out how the state machine worked, I was able to optimize the whole movement system, and it's now way more fluent. It doesn't have the bugs that it had earlier. I could add all the little effects, the dust effects, way easier. Something that I really like, and you have to pay very close attention to the character, but the moment the character lands and starts to run immediately, it goes into this little land while running animation. Look, see? Like it's doing this little duck, and then it still runs. That's like a detail that I'm very proud of, and it was so easy to do with the state machine. There's also a landing animation when you just land from an idle point of view. See? It's just skidding animation. There's another detail that I really like, because this game isn't just about fighting. There's also lots of dialogue and friendly NPCs, and I don't want the character to be like aggressive constantly, but I also don't want it to look like this when it just fought an enemy. So I have this aggressive mode. Whenever you fight, it will go into this aggressive stance for just a couple of seconds. And then when there's no danger around, it will go back to the more friendly posture. I also redid the running animation. I wasn't happy with it at all. I think the character didn't really look like the same character when it was running. While it is an improvement, I'm still not happy about it. If you look at the feet, it's way too much glued to the floor. So a future running animation will bounce a bit more into the air. Also, any other animation is still a placeholder, and you can clearly see when I do, for example, the forward air. And I really think it's like the optimal way to optimize your animations in an actual prototype. The real eye-opening moment was how fast I was able to create a combo system compared to the system that I built based on my spaghetti code. Because in the earlier version, there was like this punch logic within every other code, and it had to check like different windows of when you were able to combo, together with checking if you were crouching, jumping, not in idle. Everything broke down. And with the state machine, it was simply a matter of when you were attacking during a attack state, you go to attack 2, and when you are attacking during a attack 2 state, you go to attack 3. It's so easy. It's very small pieces of logic within a punch state. So yeah, a idle state, a punch 1, 2, and 3 state, then you go into a aggressive idle animation. There is a jump and a fall state, and I took those two separate because then you can have also a fall state without jumping by just walking off a platform like this. Looks very cool. Oh, I totally forgot about 2 states. There's a crouching state. You go into a shell. And there's also a crouch out or shield out state. I'm not sure how I called it. What a little animation that takes care of getting out of your shield. And there's the uppercut. Boom, boom, boom.
Nice.
Very cool. I really like it.
Sick.
And now we are going into really nerdy territory for any Super Smash Bros. Fan, but I specifically like the back air of many characters in the most recent game, especially Sonic. Sonic has like the most satisfying back air. It's like this one. It feels so powerful. When he's doing the kick, it also does a little spin. You can see it way better when you're on a platform. And now to get even more nerdy, you can also do a reversed back air that looks something like this. It's basically you running, turning, immediately jumping, and then do the attack. Therefore, you still have the forward momentum and you basically do a back air while going forward. It's a reversed back air. It will be the most powerful move in the game, but also one of the most difficult ones to pull off. While I'm still working on the details on how the combat should work, roughly speaking, I think the crouching will only be for things that are falling from the sky, for one-time attacks from enemies or the environment. It won't be useful for multiple combos from the enemies because I will make it so that the shield breaks. Not literally, that will be very, very gory, having a turtle without a shield, but it will break out of its shielding animation and it will go into this staggering state, which makes you very vulnerable for follow-up attacks. The explosion effect won't stay. That's just temporarily, because the combo system, the 1, 2, 3 hit, will make it so the enemy gets staggered. And from the staggered state, you can launch enemies in the sky, and you can, for example, combo into a back air. I really want to make it so that you won't be able to abuse one attack just to spam it over and over again. While the uppercut is very strong, it won't work at enemies that aren't staggered, because it's a very slow attack, and any enemy will see it coming. So the moment you press the uppercut, they will just block. So I really want to make it so that every move has its benefits in a specific situation. Nothing is final, obviously, especially the animations, as you can tell. They are very rough. But I just really wanted to work on the combat. And especially the back air, this move. It's just so satisfying to pull off. Like I said earlier, this is not going to be an in-depth tutorial on how to implement the state machine. I am thinking about making my own tutorial because I made quite some adjustments to make it work for a game like Aiden Jr. So make sure to subscribe if you want to see that one. But with that out of the way, let's take a look at the setup. So again, we are now looking at the player scene for a game like Aiden Jr. So make sure to subscribe if you want to see that one. But with that out of the way, let's take a look at the setup. So again, we are now looking at the player scene, and right over here is the state machine. So within this state machine node, you will find all the different states as like child nodes. I really agree with Shaggy that this is the most Godot way to go about this thing, because this is basically Godot's philosophy, having nodes in nodes. And if you go through all the state nodes within the movement state machine, you will see in the right sidebar that all the properties change. So these are basically the sibling states that the selected state right over here, in this case the idle state, can access and also can return. And by returning a state, it will basically swap itself with the next state. It's probably better if I show you in code. So right over here you have the variables that you can set in the sidebar. This is the enter function, a function that only gets fired once the state gets active. And in the process input function, you can define to which input the game should listen while being in this specific state. In this case, when you are in the idle state, you can jump, you can... This specific defined the state gets active.
Super. What the fuck is super? So another function he has?
And in the process input function, you can define to which input the game should listen while being in this specific state. In this case, when you are in the idle state, you can jump, you can move, you can crouch, you can attack, and you can do an uppercut. And that's why it is so easy to exclude code in a specific state. I can simply just delete this and the character can no longer crouch, jump and punch. And then you have the process physics function. It applies the gravity and some very basic functionality to go about the aggressive idle state and the default idle state. Normally you don't have to do this, by the way, having to play specific animations in the code itself that belongs to a specific state, because you can just put the animation name as a property. But in this case, I have two separate idle animations, the aggressive one and the normal one, and I didn't feel like making that a separate state because there's no other logic to it. And that is actually what it's all about with the state machine. You are connecting, chaining different states depending on input or any other logic by simply returning a state in the current state's code. For example, if you listen to the get jump input, you can return the jump state. So the get jump state will get loaded. It will also play the animation that is set right here in the properties. And then you will have the different logic that only belongs to the jump. For example, if you also press attack during the process input of the jump state and the direction has a specific match, then in my game the character will do a backward air attack or a forward air attack or a neutral air attack. But as you can see, the code file is not ridiculous.
I knew I heard nair somewhere before. That's neutral air.
Long. And if you compare that with my old code file, it literally has everything that belongs to the player in one big file. And it really gets messy. Right over here, I'm listening to animation states. I am also playing the animation. I'm setting properties. In this if statement is another if statement. Then there's an else with an if in an if. There's an else with even another if in it. It's it's really duct tape spaghetti code, and it kind of worked at the beginning, but after a while it was simply impossible for me to implement the combo system because it got so messy. And speaking about the combo system, that's actually very easy right now. In the idle animation, right over here, I simply listen to the get attack input, and if that returns true, I return the punch 1 state. If you press attack another time within a certain combo window, I simply return the punch 2 state, and so on. Yeah, I think the combo system really showed me the power of the state machine. So on Saturday, I think I worked 4 hours on the combo system without success, and on Sunday I made it work in just half an hour by implementing the state machine. But again, if you want to learn more about it, go and watch the Shaggy Devs video, and also subscribe because I'm going to make my own video that applies to a 2.5 3D game. So what's next, you might ask? I'm not completely sure. I'm currently working on the art style. I want the platforms, the 3D objects, to look a bit more in line with the character. Those are too far off currently. Next in line would probably be the combat system. We need those crabs and those bees to do some attacks and to fly and walk around in the world. And that's going to be a big challenge. I've never handled such AI, so I'm pretty sure that's going to result in similarly interesting weekends, I suppose. Make sure to like, subscribe, and I see you guys around in the next devlog. Bye bye.
Hell yeah. Oh shit.
Trying to record.
Look out. No! He got mauled to death that very same night.
Here's an updated look at how I like to do state machines in Godot 4. I'm going to go
Oh yeah, thank you.
over some simpler starter techniques today just to get you off the ground, and in the next video I'll go in depth about techniques you can use when today's examples don't cut it anymore. Also, as a side note, if you're unfamiliar with the general idea behind state machines, I'll link to a previous video down below where I go over what they are and why you may be interested in this technique. So now, let's dive in. The simplest way to manage state is by using an enumerator to track which state you're in and branch your code using a switch statement where...
Alright, well, let's see what he's got.
Hello there. few weeks ago,
Actually, wrong video, my bad.
Will certainly come.
Let's see.
The finite state machine is something that plenty of game developers have never heard of, but have almost certainly come very close to implementing a crude version of at some point or another. It's a fundamental design pattern that's fairly intuitive, with uses in character controllers, simple AI, and even UI components. But many, including myself, wouldn't come up with the complete implementation of it on their own without guidance from those that are smarter than us. It's important to understand this design pattern because it offers a lot of bang for your buck, letting you write code that is cleaner, easier to maintain, and easily expandable for little effort. So this week I'm going to kick off a two-part discussion on state machines and how to implement them. In this first video, I'll talk about why you should care about state machines and introduce the state pattern, which will show us how we can implement a state machine in code. But I'm going to stick to pseudocode this week so we don't get too bogged down in engine-specific details. Then in the next video, we'll step into Godot and look at how we can implement the state pattern there, taking advantage of the features that the engine offers. So let's dive in. To kick things off, let's first talk about what our code might look like without the state pattern so that we can understand the benefits it offers. Consider a simple platformer game. We start off with a clean project and throw in our idle animation as the default state for our player. We then add a run animation and some basic code based on what input the player is pressing to switch between the two. So far so good. But now we want to let the player jump. And if they can jump, then they can also fall, which oftentimes will be a different animation in your game. So we go ahead and add animations and code for jumping and falling states. Except that, as written, the jump animation will only play for 1 frame before defaulting to the falling animation, and the player can no longer move when they're in the air. So we need to do some more checks to this code and add in a little bit of refactoring, and we might end up like something what I have here now. It's serviceable, but what if we want to add in a double jump, or maybe an attack? For the double jump, we'll need a variable to track whether or not we've already double jumped, since at this point all we know is whether or not we're in the air, not what we've done while in the air. So we add that in and some additional checks to handle the double jump. For the attack, we'll need an animation, we'll need a timer, or some sort of callback so we know when the attack is over, and so that we know when we can transition to the base states of idling, moving, jumping, or falling. We might also want to show a different animation when in the air versus on the ground when we attack. And so you can already see where this is going. Pretty soon we'll end up with a long stretch of code filled with nested if statements and half a dozen or more variables that are used solely to track different states. It's ugly, it's error prone, it's hard to debug, and later on if we decide we want to go full Metroidvania and add a dozen more power-ups and abilities, it'll become a giant mess of hundreds of lines of code that we'll never want to go near and we'll probably never get it completely bug-free. So, let's take a step back, put down our keyboard, and step over to the whiteboard for a moment to figure out what it is we're really trying to do. And if I ask you to draw me a flowchart showing
This is exactly what I did. This is really good for me, potentially.
the rules of our character and what they should do and when, you could do so pretty easily. Drawing our basic set of idle, walk, and jump states, we might end up with something like this. And note that I've reworded a few of our checks just for the sake of brevity here. The overall functionality is the same. And so now we can further expand on this to include a fall state, a double jump, or whatever other states we want. We know what the rules of our character are, and they're not even that complicated, since most of what we have so far is just depending on whether or not we're on the ground. What is complicated is telling the computer the rules for switching between states when we have no concept of state. As we saw with even our basic platformer codebase, a series of if statements just doesn't cut it when we have more than 2 or 3 states we can be in. But what we've just done with our flowcharts is describe a finite state machine, which can be summed up with a few simple rules. First, there is a fixed number of states our character can be in, such as idling, walking, jumping, etc. Secondly, the player can only be in one state at a time. You obviously can't be walking and idling simultaneously, for instance. Thirdly, each state is responsible for doing one thing and one thing only. So the walking state lets us walk, the jumping state lets us jump, etc. And finally, the active state receives inputs, logical inputs in this case, and not necessarily key inputs from the player, though those are also valid, and it then takes these inputs and follows its own rules as to when to transition to another state. As an example, if we're falling and landing on the ground, that's one input into the machine, but then we can either begin walking or idling depending on what keys, if any, the player is pressing. And that's it as far as the concept of a finite state machine is concerned. If you can draw the behavior you want with a flowchart, you can make a finite state machine out of it. And as one additional note before we look at how to implement a finite state machine, I'll mention that you'll often see people, including myself, use the term finite state machine and state machine interchangeably. For most people's purposes, the two are the same thing, as even Wikipedia redirects the term state machine to finite state machine. But a state machine is technically the more generalized form of the finite state machine, and it does not necessarily have a fixed or finite number of states it can be in. But that's as much as I can speak to the distinction, since I'm not an expert on AI and or computational models. Get your local math professor or computer science professor drunk if you really really want to dive into the differences, especially in a game development context. And so we've established that finite state machines are great for laying out and organizing the flow of state in our game, but we still don't know how to actually implement one in code, so let's do that now. In the most basic form of implementation, if we have a fixed set of unique states and only one can be active at a time, we can get away with representing our current state using enumerators and branching our code as needed. This lets us turn our player code class from this into this. It still doesn't completely get rid of the problems we ran into above, as we still have to manage several variables and timers for different states, but it does at least let us segregate our logic for each state into separate functions and give us a fairly readable stretch of code once more, and makes it very clear what our current state always is. And with this setup, we can at least follow the branches of code easily enough that we can get where we need to for low mental effort if we need to debug something. This is the version of the state machine that I figure some of you have either implemented or come close to implementing in the past, as taking a glob of complex code and breaking into smaller functions is a pretty natural step to take as your code base grows. The enum is just one more layer to help us keep track of everything. But you'll quickly outgrow this implementation for many or even most use cases, but it is worth mentioning as it's a great fit for very simple objects. In fact, I find myself reaching for this technique when I'm making an object with a basic on-off state, such as a door or a switch, or maybe a simple turret that's either scanning the room, firing on a target, or recharging its shot. So this method is okay and is useful, but there is a better way to implement a state machine, and that's where the state pattern comes in. The state pattern describes an object-oriented way for an object to change its behavior on the fly based on the inputs it receives. The term object-oriented is the giveaway for what we're about to do. Create an interface representing a generic state, implement the interface with a class for each state, let the parent entity, our player in this case, delegate all state-dependent logic to the class representing the active state, and then provide a way for the states to transition to one another. So let's look at each in order. First, we create an interface to describe a generic state that has a virtual method for everything we normally have a switch and/or if statement controlling. Implementing input and update methods is a good start, but you may also want to connect your physics controlling generic state that has a virtual method for everything we normally have a switch and/or if statement controlling. Implementing input and update methods is a good start, but you may also want to connect your physics update loop if it's separate from your regular update loop, like it is in Godot and many other engines. You may want to connect your collision callbacks, etc. Everything that would need to act differently based on the state we're in gets a method. That way we have a consistent interface our parent entity can rely on and reference. We then need to create a class for each state that implements the state-dependent logic. In our case, that would be idle, walking, jumping, etc. We'll use our jump state as an example for this code block, excluding the code for transitioning to another state since we'll come back to that in just a moment. With each state now identified in its own class, the parent entity, our player class, just needs to track what the current state is and delegate all logic to it when an event occurs. Our base class can now look something like this. So we now have the general idea of how everything works, but we've left out a pretty important detail: how the state change actually happens. And there's actually a few different ways to implement this, but I'm just going to show you my preferred method today. So let's go back to our interface and now make it so that each virtual method can optionally return a new state to the player class. This makes our jump class now look like this. And every time we want to change states, we'll simply return a new instance of the state we want to transition to. Updating our player class, we can now check for a returned value after each call to the active state. And if we're returned a new state, we switch states and delete our old state. Now, this method results in a fair bit of data churn, but it generally shouldn't be a problem for performance. We won't look at alternative implementations in this lesson, as I want to keep things as straightforward as possible and not overwhelm you with every possible way of implementing the state machine. But if you do want to prevent this churn, you could also consider using static states if there's only one instance of an object in the world, such as the player in a single player game, or keeping one instance of each state in the memory and using a service to get a reference to each one at runtime and resetting their behavior whenever you switch to them. And in fact, this second method is what I used in Liberation Mutagenics, my Lemmings-esque game that had multiple layers of state machine to sort through. There was one layer for the genetic state each character could be in, and then there was another one for the specific action they were currently doing while in that genetic state. And so, we're already in a pretty good spot with our code, and you could use it more or less as is, but let's do one more expansion of it and add logic that runs when we enter or exit a state. That way we can easily do things like switching animations upon entering a new state, canceling any asynchronous calls that may be running when we exit the state, etc. And doing that, our interface turns our jump class into this. And note that we still have to implement the exit method even if we don't need it for this particular state. This is important so that our player class never has to concern itself with what methods are and are not implemented on a specific state. But at the end of this video, I will mention another way that you can implement this without having to have an empty method in every state if you don't need it. But speaking of our player class, it now changes to this. Nothing too crazy. We just now let our previous state exit before switching to the new state and then calling its enter function. And now we have a robust state machine. Expanding on this, say to add a dash attack or ground slide just means writing a new class that implements our standard interface. No other parts of our code will care, and they just have to instance any new classes if and when they should switch to them. And so this ends up being a lot cleaner and neater than what we were doing previously with lots of nested if statements and even the enumerator operation. I'll also mention that you may find yourself duplicating a lot of code, or maybe just doing the same thing each time you enter a state, just slightly differently, such as playing an animation and a sound upon entering every state. And you may also run into a situation where, for instance, on our jump class, we don't need to call the exit method in that state, but we still have to anyways. And so in such a case, you may find it useful to create a base state class that implements the state interface and lets all of your other state classes inherit from that, just using a variable to modify reusable code blocks as needed and overriding its base implementation of the function as needed. And so for instance, it can hold the exit function, that way jump does not have to, and that lets us clean up that code just a little bit further. And that finally is all I want to talk about regarding state machines and the state pattern. There's a lot more that I haven't covered, but this should be enough to get you well on your way with them. If you want to know more, Game Programming Patterns has an excellent chapter on state machines, along with some alternative implementations of them and additional ways they can be expanded upon. I'll link to that in the description. In the next video, we'll hop into Godot and I'll show you how we can implement a state machine there. See you then. Nodes are...
I'm gonna be completely real with you guys. I almost fell asleep like 3 times during that. No discredit the guy. It's not his fault. I'm just very warm right now and a bit more tired than I thought it was. Also, damn light turned off. But the fan's still going, but I said my fan, it goes, it doesn't do shit. That was the most like non-functioning fan I've ever seen in my entire life. Like no matter what, it always stays warm in here with that thing on. Unless it's, freezing outside, in which case, makes sense, but good lord, I was on the verge of passing out during that. Again, not the guy's fault. It's my fault for not realizing I was going to be this tired today. That being said, give me 1 second. I'm going to turn on a fan. Hopefully it doesn't make a lot of noise while I stream, so BRB. Okay, I'm back. Now you may be wondering, John, if you're so warm, why don't you just change your shirt out? I would, but I don't wanna. In fact, I lied. I would not, just because I already committed the shirt for the stream. So we're gonna stick with it for right now. Now is not the time for shirt swapping. Now is the time for action. Action being whatever the hell this is. Let's see it.
Are
Oh wait, I didn't put my stuff back in. Hold on. Hold on, hold on, hold on, hold on. Didn't have my earbuds in. 1 second. 1 second. There we go. Alright. Back to this. Oops. There we go. Nope, that's not. There we go. I opened this up just because I wanted to watch this later. So, back to this.
wherever you have state-dependent logic that needs to run. There's nothing Godot specific about this implementation, but I do want to bring it up for the sake of completeness, as it can really come in handy whenever you have an object that just needs a little organizational help. The turrets in my game Liberation Mutagenics, for instance, use this technique of state management since they only have 3 simple states they can be in.
Also, the thing I want to mention, by the way, my music stopped at some point. I don't really know how. But it's fine for right now. We don't really need it.
Scanning for targets, firing on a target, and recharging. In fact, let's recreate a bare-bones version of a turret as an example of what we can do with this form of state management. Our turret will default to a scanning state where it waits for the player to enter its view, fire upon the player when it sees them, and then become dormant for some amount of time while it recharges before going back to scanning for the player. So here's the scene, composed of just an animated sprite 2D node for graphics, a raycast 2D node to detect when a physics body passes the turret, and a line 2D node so we can see where the raycast 2D node is scanning. Since this is a demo, we'll just change animations to show what state we're in and move on without worrying about making the player react or anything like that. And here's the code. The possible states the turret can be in are declared at the top, along with references to the nodes the code needs and a few variables to help control everything.
See, hold on a second. Shit. Do this. So my Steam's not open, so I can't open my video right now. Hold on. Come on. Go. Alright, we're good to go. So I want to look at real quick is want to look at the view line stuff he was talking about. Huh? What? Oh, this is the Judy scripted tutorial project. Hold on. I was looking for the other thing. Practice project. I just say okay. Genuinely don't remember. No, it's bench. My bad. How you doing, baby? Doing good? I am proud of what I managed to get done here, though. So once again, if you look at this, that's not the right scene. Whoa, that's wrong. I mean, it's right, but it's not supposed to stretch like that. Okay, hold on. Let me, project settings. main scene. This one. World. Yeah, this. I'm proud of this. I sure it's very bare bones. It's not that great. Solution gets broken if you go too far to the side. And all that, but like, this is parallaxing. I think I did a pretty good job with and everything. I thought I had an idea that I could just change it to where the like everything is on. See, like if I do this, it breaks the illusion, but I could make those on different layers. In theory, like, I could make the background and foreground objects different layers. I just have to copy and paste them their own layers and save them as their own images. That way I could parallax this a lot more and make it look a lot prettier, but like the background, like the buildings in the back are further back than the ones in the foreground. But I think overall I did a pretty good job with this. And that's where it starts breaking down at. But anyways. I need to fucking find that thing I was looking for. Go on to see the Raycast note on that little slime guy. That's for the Brackeys tutorial, but it's not this one. That's a GD script. Oh, first game project. There we go. That should be it. Let's see here. That's it. Yeah, this is it. So I wanted to see if I can add the let me call it like line, I think. Line 2D. 2D polyline that can optionally be textured. 2D, the node draws a 2D polyline, i.e. a shape consisting 0 points connected by segments. Line 2D polyline, i.e. the segments are not infinitely thin, is intended for rendering colored and optionally textured. Warning, certain configurations possible to draw nicely, such as very large and very sharp angles. In these situations, the node uses fallback drawing logic to look decent. Note: Line 2D is drawn using a 2D mesh. Awesome, I think. Why is there no audio for this? Uh, what the hell am I supposed to do with this? I get that, like, I'm kind of getting sidetracked here, but what is this? Uh, Ah, there we go. That's why I couldn't see it. Negative. Actually, hold on, let me... Yeah, so I can bring this down a little bit. What the hell is the central point on this thing, actually? Negative 12? Oh, let me, what? Okay, so it should be 6 then. Never mind. That seems about right. Uh, negative 7 too. Perfect. And then I could put this on this one. But, you know, change its... What the fuck? Control C. Right. Hold. Yes. Uh, so why is this not what? Oh, there you go. What? Oh, the fucking, what are you doing? Okay, that should be good. Yeah. So I wanted to see this. Let's get that width up a bit. Uh, let's see. There you go. You can see a bit better as to where it is. It's still not big enough, I'll be honest. Do 0.5. Where? What? Oh, there. Keep losing where these things are at. There we go. Basic exactly where it's at. Everyone don't see the recast at the bottom right. Hold on. Uh, no. Hold on, I'll figure this out somehow. Use the points segment. There we go. Zero this? Nope. What is that? -6, I suppose. Nope. Also no. What the fuck? 12? Oh, I guess so. Hold on. Let's see, 13. What are these? What are the actual breakcasts? -10 and 7, I guess. Okay. Uh, uh, I try -13 and 3, I guess. -13. That isn't even remotely correct. Fuck. Nope. So that'd be 17. That'll be 13. I'm just assuming. There we go. Oh, by the way, when I press, I know it's in the title. I never talked about this. Look at this. Where I was running space before, and it would just type it in every time. Not doing that anymore. I don't know why. It's just, yeah, it's fixed now, I guess. I'm happy it's not anymore. It's just like, it's like over time, it just became less and less until suddenly just stopped doing that. I don't know why. I ain't complaining. Control S. You're at this. What? Oh, that's not what I'm actually about to do. I wasted a lot of time doing that. That was completely pointless. Well, it wasn't really. I was trying to figure out how the line thing worked. I kind of got an idea. What's it doing? This. There we go.
Majority of this code is just about doing whatever each state needs to do, as there's very little overhead here. During the process and physics process calls, we run different logic depending on what state we're in, and change states via the change state function so we can handle any setup or teardown that's required when changing states, such as playing an animation or resetting a timer. This technique is simple, effective, and makes it easy to expand the codebase over time while keeping things neater than using a bunch of if statements and conditional booleans to figure out which state the object is in. It's definitely a go-to technique of mine, but when I have more than a fairly simple object or set of states to manage, I do prefer to reach for a more robust implementation, which I'll discuss now. As opposed to a purely code-based solution, which you will see a lot of the time, my preferred way of implementing a state machine in Godot uses a node-based approach. This approach consists of one node managing all of the states, and a number of child nodes as the actual state implementations. The parent object delegates logic resolution to the state manager, which then delegates to the active state and handles state transitions as appropriate. You can certainly build up more or less the exact same thing using code, but I do like the node approach for a few reasons. The biggest of which is that it lets me take advantage of the features of the Godot editor. With nodes, I can export variables to easily tweak them without having to go into my code, including for connecting state transitions. Plus, I can visually inspect my state machine in the editor. These two together make it easy to reason about and adjust my state machine as I go along. This technique also lets me be lazy and reuse my states on different objects by just dragging a node into the editor and putting a script on it. And most subjectively, I just like this approach. I find it intuitive and feel that it meshes well with Godot's approach to game development. So with the why out of the way, let's talk about the how by walking through a state machine designed to control the player character in a game, since character controllers are a common use case for state machines. We'll focus on only a user-controlled player for now, as there's already plenty to cover, and making this code work for multiple entities, including NPCs and enemies, will require introducing some additional concepts that I'll talk about in the next video. So looking at the player scene, the player is a character body 2D node with a collision-shaped 2D node for physics, animated sprite 2D node for graphics, and the relevant state machine nodes attached to help it operate, all of which are just plain node types. The script on the player looks like this. Not a lot to it, as the player really just delegates any state-dependent logic to the state machine for further processing, such as with the physics process or unhandled input functions. It does also pass a reference to itself during the state machine initialization, so that the states can have a reference to it and therefore control it directly. There are ways around this if you don't like the idea of a child node controlling a parent, which I normally would agree with, but since the states are essentially hot swappable brains for the player, I'm okay with it in this instance. Moving one step down the hierarchy, we have the actual state machine. This component is responsible for managing the state of the parent object, delegating to the active state, and handling any state transitions that may be required. Upon initialization, the state machine passes a reference to the parent to each child state and enters the default starting state. And in case you're wondering, you could let the state machine reach up the hierarchy to find the parent rather than having the reference passed as a parameter to the initialization function, but that can be an error-prone design if every scene isn't structured exactly the same, so I don't generally recommend doing that. The rest of this node is essentially as you would expect with the state pattern. Each state node can optionally return a new state to transition to after processing an event. If a new state is desired, the previous state gets a chance to clean itself up with the exit function before the new state is marked as active and its enter function is called. So now let's look at what the state nodes are actually doing. At the heart of every state node is the state class. This class is never directly used unless you just wanted to have a no-op state for some reason, but having class name at the top still makes it useful to us, as we'll see in just a moment. Since this class is the core interface behind our state interactions, let's break it down line by line so we can make sure we understand what it's doing. At the top, class name declares a class name state in the global namespace, which basically means we can bring in all of the code here into other scripts without having to copy-paste anything or reference the exact location of this file. And it lets us make use of Godot's type system, giving benefits such as text completion, auto-filtering any exported variables to the given type, and so on. Moving on to our variables, by exporting animation name, we can easily tell our state to play an animation on the player whenever the state takes over. Similarly, move speed is exported so that all of our states can have movement if desired. And lastly, gravity is loaded from the global game settings so that we can have a consistent value on every physics object. Next we come to the parent. We saw a reference to this variable in the state machine, and here's where it lives. Each state holds a reference to the player so that it can control the player as if they were directly connected to one another. Looking at the functions next, this is the meat of the state class, though it might not look like it since it's fairly sparse. Here, a default implementation for each function that may get called by the state machine is declared, with the ones that are expected to return a state if desired, returning null by default, signaling to the state machine that a state transition should not occur. One thing that may stand out to you is that I don't use the built-in process, physics process, or unhandled input functions directly that come with nodes, and the reason is really just a stylistic preference. I simply prefer to use a separate function that I have defined and have full and direct control over. You can certainly use the built-in functions directly, along with a few calls in your enter and exit functions to toggle the processing of these functions on and off, but I just prefer to be a bit more explicit in what I'm doing. Which I guess means that this is a good time to remind you that options exist, there's little that should be taken as dogma, and over time you'll figure out what you like and what works best for you. And that wraps up this base state class. As we look at the other states, you'll notice
I never even thought of the possibility of making your own process function at all.
that not every function here is shown.
Insanity.
In those cases, that's because we're falling back on the default implementation declared in this file, which typically does nothing. From here, we just need to have an instance of this class for each state along with any of the state-relevant logic. To create a state, we can add a node as a child of our state machine and attach a script that extends our state class. Meaning, as we just talked about, we'll bring in everything we just looked at while also adding new functionality on top of it. To demonstrate this, let's look at the code for the idle state and break it down. At the top, extend state tells Godot that this script inherits from the state class. We then have a few exports for the states we want to transition to. Since we've typed them as state nodes, the Godot editor will automatically filter our options for us when we go to set these values. Looking at the inner function, here's where some of the magic starts to happen. The call to super means that we will call the enter function as defined in our top level state class, which, as a quick refresher, is defined as a single line that plays an animation for us. So by calling super, we can set our animation when we enter the state and still
Hold on, he even mentioned super here. What the fuck is super?
Since we've typed them as state nodes, the Godot editor will automatically filter our options for us when we go to set these values. Looking at the inner function, here's where some of the magic starts to happen. The call to super means that we will call the enter function as defined in our top level state class, which, as a quick refresher, is defined as a single line that plays an animation for us. So by calling super, we can set our animation when we enter the state and still run any custom enter logic we want, which in this case is used to zero out the player's horizontal velocity.
Hold your fucking horses right now. Parent class and G-script especially. Your inherited methods. Notation. Functions from an inherited class. I have class A that has a print function. Class A. Everything. With nothing. Okay, I think. Fucking hate things like this. It's like, have you looked at the documentation? Well, have you tried searching through the documentation? That shit's a nightmare. And not no shade on the people that made it, because it's really in depth and really good, but like it's so hard to sort through. There's so much you could be looking at. And hell, even when you do find what you're looking for, you don't know how to find the thing you need half the time. There's gonna be a tutorial on it.
Este video nos servirá para repasar
Shit.
la herencia. Además,
I wasn't expecting this. Very question. Okay. Well, if you speak Spanish and you need to understand what super does, well, there you go. Just for you. Yeah, let's get back into
let's
this.
look at the process input function, which is looking for the player to
I think I
either
kind of
press
understand. I think it's like pulling a function from a child or replacing one of the child's functions with something from the parent or something like that. I'm not certain. I'm just talking. I don't know. But that's what I'm thinking, at least from what I understand.
Next
The
up,
part I read so far.
let's look at the process input function, which is looking for the player to either press the jump button while on the floor, which will send the player to the jump state, or one of the movement keys, which will send them to the movement state. And lastly, we have the process physics function, which applies gravity and moves the player appropriately, and switches to the fall state in case something happens while idle and the player is no longer standing on the ground. And that's it for the idle state. To help drive things home a little bit further on how this implements around.
I like that. I like them putting the exclamation point instead of just saying not. So I was saying not, but that's I didn't know you could do that. So that's an interesting way of doing that.
The idle state. To help drive things home a little bit further on how this implementation works, let's also look at the jump state, which is pretty similar but does have a little bit more going on. Breaking it down again, you'll notice the top of the file is largely the same as when it was in the idle state. We state that we're inheriting from the state class, export the states we'll transition to, but now also export a new state-specific variable, jump force, to configure how hard to jump upwards when the player jumps. When the jump state is entered, we let the parent implementation go first, setting the appropriate animation, and then set the player's vertical velocity to the jump force we defined, just flipped since Y values decrease as you move upward in Godot. Why not just make the jump force negative from the start? Well, again, this is just a bit of a stylistic thing since I just prefer to define a force that will act on something in the positive and then orient it correctly when needed. It is perfectly valid though to just set the jump force to a negative value and skip this step. Moving on to the physics update, during the update we let gravity work its magic and switch to the fall state if the player is no longer moving upward. Otherwise, we read in the player's input to let the player move around in the air as desired, update the physics body with move and slide, and then check if we're on the floor. If so, we'll transition to a move or idle state depending on if any keys are currently pressed. If not, we'll return null and keep the jump state active for another frame. And that's it for the jump state and states in general for this implementation. I'll save you the tedium of going through all of the other states just to see more or less the same thing over and over, but if you look in the sample project, you'll see a similar pattern of overriding the functions we care about, ignoring the ones we don't, and responding to inputs or events where appropriate. And so with what we currently have, you can easily set up a simple character controller to use in your game and flesh it out as appropriate. But that's about all you can do right now. In the next video, I'll show you some techniques for building a more advanced state machine that's capable of a lot more than what we've seen here.
Ooh. There's some monitors. I was just in this.
In the last video, I showed some
Oh, I'll look at this real quick.
out of the box, Godot gives you all sorts of ways to monitor your
Shit, I didn't even see this. What the hell?
game's performance and behavior. You can monitor the FPS, draw calls, memory usage, number of objects, and much more. But you can also define your own custom monitors to track whatever's of interest to you, something I've done on Unto Deepest Depths to help me track areas of interest for both performance and balance. To monitor custom metrics, you can simply call performance.addCustomMonitor and provide an ID for your metric and a function that can be called to provide the current metric value. This function will automatically be called periodically at runtime, so while you do need to store the value you'll want to return somewhere in your code, you only need to store and therefore your function only needs to return the current value. Godot will take care of showing you the historical values in the chart. And it's worth noting that while both floats and integers are supported, these values cannot be negative and will be clamped to 0 if provided. As an example of using custom monitors, in Unto Deepest Depths for instance, I cache basic navigation data during battles to speed up AI decision making. When adding this feature, I decided to monitor it so that in the short term I could easily verify the cache was working correctly, and in the long term to have an idea of how large that cache typically gets. So in my navigation service, I call performance.addCustomMonitor to register the monitor, and then define a getMovementCacheSize function to return an integer of how many cache entries there are. With this setup, I can now monitor how large my navigation cache is by simply opening up the debugger tools, going to the monitors tab, and checking my custom monitor. I also use custom monitors for monitoring how long a level takes to generate, how long the AI takes to process certain information, and even to track game balance, which might seem a bit odd at first, but is actually pretty straightforward. I use a point buy system in Unto Deepest Depths to generate levels, meaning I convert the player's progress into a numerical value, assign point cost to each enemy type, and then purchase enemies with the points available based on the player's progress. This means that as I've been testing and balancing the game, I can, at any time, open my custom monitor and see the exact budget that was used to generate a level, making it easy to understand why a level was generated as it was, and intuit what balance changes may be needed to make things fairer. For a few additional usage notes, you may have noticed that in demoing my monitors, they each fall under a specific category, such as navigation, AI, and level. That's because I'm using a built-in feature of custom monitors where if a slash delimiter is present in a monitor ID, the text before the slash will be considered a category name, the text after will be considered the monitor name, and at runtime all of the performance monitors will be grouped into their relevant categories, making it easy to find what I'm looking for. If you choose to exclude a slash or include several slashes in your monitor ID, your monitor will end up in the default custom category. Another thing worth noting is that you can only add a monitor once, with subsequent attempts to create the same monitor resulting in an error. If you are unsure if a monitor has been created, you can call performance.hasCustomMonitor with the name of the monitor to check. Similarly, you can call performance.getCustomMonitor to programmatically access the current value of a given monitor, but that's left as an exercise for the viewer.
Oh yeah. I didn't need to watch that right now, but I did it anyways because I'm so smart and cool and amazing. Ooh. Oh.
Hey everyone, welcome back. In this video, I'll show you how to set a texture for a UI button in Godot.
This guy's voice AI kind of sounds like it. Automatic dubbing though. Hold on. No, that's what it was originally. What?
Specifically using a texture button. If you've created the button but can't figure out where to assign the image, you're not alone. Let's fix that in under a minute.
Okay, I know how to do this. I was just kind of confused. I just wanted to look at this in general. There we go.
Some
On to
basic
this.
techniques for managing state in your game. Today, I'm going to show you some techniques you can use when you need something more complex than just a simple state machine. But be warned, there are a lot of ways to make a state machine, and this video is by no means an attempt to be anything close to an exhaustive look at the subject, but rather address a few common pain points and show some techniques for dealing with them by upgrading the state machine I introduced previously. So to kick things off, let's first discuss a few concepts that can be used to solve a variety of problems with a growing state machine, the first of which is dependency injection. Dependency injection is about supplying dependencies at runtime rather than hard-coding them, and is actually something that already exists in the starter state machine. Recall that the states declare a parent variable to hold a reference to the player, but that the variable doesn't actually get set until the player sets it in its ready function. That's dependency injection. The states declare they depend on having a reference to a player, but not any specific instances of a player. Compare that to if each state did have a hard-coded path to a specific instance, which is not very flexible as our code is looking for a singular node to control and is also requiring our game tree to follow a specific structure. Dependency injection frees our code from the details of how we get a reference to an object. With this concept in mind, one technique for making state machines flexible is to design them so that they can use different instances of the same type. If all of your game objects use the same physics implementation, such as Godot's character body classes, you can design your states around this class for handling movement and other physics logic, declare that's the type of object they'll control, and share that same physics code across your game. The current state code relies on a player instance, which is better than nothing in case we want to have different player-controlled characters, but it could easily be made more generic by letting it control any similar character body 2D node, which is the type of physics body the player is. Updating my previous state machine code, I just changed the declaration of the parent from player to character body 2D in the code for both the individual state declaration and the state machine. As the player class already inherits from character body 2D, its script doesn't require any changes. And now our state machine can move any similar physics body, but there's still more we can abstract out. Let's also update the reference to our animations, which are currently referenced as a child of the parent node. Rather than always assuming there's an animations property on our parent, we can create another dependency in our state class for the animated sprite 2D class, which should be sufficient for a variety of animated entities, including the player. As this is a new dependency and not just replacing an existing one, we'll need to update the entire chain of initialization this time, from the player to the state machine to the state. And with that, we've already made our states more flexible as we can support different physics-based objects and we
Oh,
no
hell
longer
yeah.
make any assumptions about the structure of the parent object. But there's still more to do before we can really make use of our state machine on other objects. For example, our original movement code has several lines that reference user inputs, which is problematic if we want to use this code on any non-player characters. Ideally, we also don't want to have to write new movement code for every different type of movement input. One option here is to abstract away the specifics of how movement is decided, as our state machine really just needs to move how we tell it to. How that decision is made is beyond what the input-related code cares about. So let's establish a contract of sorts defining how the state machine can query some other object, the specifics of which we'll come back to in a moment, for information about how to move, and update our state machine to use this new object accordingly. Really, this contract is just an interface, but since Godot does not have support for interfaces as of version 4.1, we'll have to get a little bit creative with the implementation. One option is to declare a class with some basic no-op functions in it that your components can inherit and override, much like what our base state class is already doing. Another option is to use Godot's support for duck typing and just use consistent function names on everything without worrying about declaring specific types. In my own projects, I typically prefer the class-based approach just because I like to have the benefits of type hints, auto-completion, and so on. But to help cut down on the boilerplate code today, let's just go with the duck-typed approach and decide on a few common function names we'll implement. Get movement direction will return the desired direction of movement for the character. As the sample project is a platformer, we only care about the movement vector along the x-axis. But if you want to expand this to support two-dimensional movement, you can of course just change the return type to a vector2 and update your code appropriately. Once jump returns a boolean indicating if the character wants to jump right now. I use the term wants as this function only tells us if the jump input has been triggered, not whether or not the character can jump at this specific point in time, as that is something the state machine should get the final say over. And in case you're wondering, you could condense these two functions down into a single function, returning a vector2 where the y value represents whether or not jump is pressed, but for demonstration purposes, I'm going to keep things just a little bit more readable and keep them separated. With our functions defined, the question then becomes where do we implement these functions? We could implement them on the parent object directly, but that would hurt code reuse since we'd have to add the code to every entity in our game. To get around this, we could do an inheritance-based approach and let our parent objects inherit from some top-level class that implements the functions, but if we need to implement multiple interfaces that vary between objects, or just have multiple implementations of different interfaces, that can also become problematic as our inheritance tree has to grow to support different feature sets. Instead, we can go with a component-based approach, where we simply add a node to our character object that has a script implementing our desired functions on it, and pass this node to our state machine. The benefits of this approach is that reusing code is as simple as adding a node to our scene with the desired script on it, but it's also easy to change behavior on a per-entity basis without having to make any modifications to the parent object. Just replace the script on this node and you're done. So with our plan decided on, let's now create two components implementing this interface. One for the user-controlled player, and one for a very simple AI-controlled character. First up, let's look at the player component, which really just wraps basic input functions behind our interface. We can then make a child node on the player, attach this script to it, and as we'll need this in pretty much every state, we can pass this into our state initialization code alongside the references to the parent and animation nodes. Now we can access move component wherever we need to. If we want to update our move state, for instance, we could swap out the old input code with our new function. All that's different is we now ask the move component about how to move rather than polling the input class directly. Hopefully you can already see the benefits this technique offers. We can now swap out move component for anything that returns a boolean for jumping and a float for horizontal movement and have our state just work. To demonstrate this, let's make a very old school AI controller that's just about as simple as you can get. This component keeps a reference to the parent character body 2D to implement a simple controller where the character moves in one direction until it hits a wall, then starts moving in the opposite direction. Once jump is still implemented since that is a requirement of our interface, but since this character isn't allowed to jump, we just always return false. Put this on a new character to see it in action, or even just replace the component on the player and watch it now automatically move around. That's the power of abstracting state functionality into components. One codebase can now support any movement controller as long as it implements our interface. The last concept I want to introduce is that of hierarchical state machines, which involves using inheritance to make your state logic reusable across multiple states, something that, again, we're actually already doing in my starter state machine code. Recall that the code for the base state implementation has an enter function that automatically plays an animation when the state is entered. Since our other states inherit from this class, we only have to write this code once and then can reuse it across every state. Some states define a custom enter function that extends this functionality, but others don't. That's the idea of a hierarchical state machine. Functionality defined in the superclass that you can fall back on, extend, or override as appropriate. For instance, you could throw the code that reads from our movement component into a separate function to make it easier to modify or override in a subclass. To demonstrate this, let's implement a dash state, which will work just like the movement state, except the player is locked into this state for a fixed amount of time and cannot jump to exit this state early. To start, let's add two new functions in the state class for reading inputs from our movement component so that we can override them later on. Our move state and any other state can then use these functions similar to when they use the movement component directly. If we want to make a dash state in a hierarchical fashion, we could subclass the move script, override get movement input to return a constant value when we should be dashing, override get jump to always return false so that we can't jump out of the dash state, track our time in this new state so we can automatically exit when the dash duration has elapsed, and then let the parent move state take care of the actual movement logic. With that state defined, we just need to add it to another state node and update the states we want to be able to enter the dash state from, in this case probably the idle and move states. And that's an example of using hierarchical states to override and modify behavior from a state. While the dash state does still have a fair bit going on, we do at least avoid having to re-implement the basic movement code for this one. Now I'd like to shift gears a bit and talk about some common pain points you may find yourself in with state machines and some potential solutions for them. Again, this won't be exhaustive by any means, just an attempt to share a bit more based off of questions I've gotten over time. If you've got any techniques or design patterns you like to use for solving state-related issues, do feel free to share in the comments. One of the most
Once again, I'm falling asleep during this. I don't mean to. But I realize I'm a lot more energized when I'm actually doing stuff. I really should have just been writing stuff down while this happened. But if I start doing that, I start getting distracted. I start... Oh, man. I start, getting sidetracked and stuff. It's just a whole mess. I'm sorry, guys. I don't know if we should watch these next ones because you kind of just sped through a lot of things.
Hello,
but, I mean, I
and
guess we
welcome
did
back
kind
to
of
the channel.
some stuff.
Today I'll be walking you through the process of turning your game from this to this. We'll be adding 3D enemies with animations, pathfinding, custom
Oh, wait, we're not done yet. I just want to look at this real quick.
collision shapes for FPS games, and even spawn points. So strap in, grab your favorite drink, grab your favorite game engine, and let's get right into this. We'll be getting our models from Mixamo, which is
Dude, let's grab that auto. You guys remember that? I remember
a
that.
huge free 3D character and
Fuck yeah.
animation library provided by Adobe. The process here is pretty simple. Just choose the character you want to use from their selection. In this case, we'll search for a zombie character. Then head over to the animations tab and pick the ones that you want to use. All of their animations can be used on all of their characters. In this case, we're only looking at animations that are tagged zombie. For example, we're definitely going to need a run animation, so we're going to click download here. We get a couple of options here. For the format, we're going to use FBX, which is not supported by Godot by default, but we're going to need to go through Blender to combine all of the animations anyway. Hit download, and then we're also going to get a stand-up animation for when we spawn the zombies and an attack animation. Under the download button, there are a couple of settings which we can use to customize the animation. So we're going to speed up our zombie attack a little before we download it. Once we downloaded all of the animations, we will open up a new scene in Blender. Hit A.
Yeah, see. You just kind of speed through stuff a lot. I mean, it's still useful, but...
Hello and welcome back to the channel.
Oh,
Today we'll
fuck
be
yeah.
doing a tutorial on shooting mechanics for an FPS game in Godot. We're going to cover gun animations, bullet movement, complex collision shapes with body parts and weak points for our enemies, as well as dying animations and enemy despawning. This video is most useful when you already have a character controller, a map, and some enemies, all of which I cover in my other tutorials, but you don't need to have seen them to understand this one. So let's dive right in. The first step is finding a nice gun model that's already in a Godot supported format, or converting it with Blender. Get it into the project files and
start that stop this
Hello
one.
and welcome back to the channel. Today we'll be doing a tutorial on implementing a hit scan weapon for your Godot FPS. We'll be covering crosshairs and hit markers, shooting animations, bullet trails, hit particles, and weapon switching. We'll be starting off with some parts of the game already complete, so if you're curious about how anything else works, you can check out my other tutorials, but you don't need to have seen them to understand this one. So let's get right into it. For our hit scan weapon, we're going to be using this model from Sketchfab made by Chouei. Right click, new inherit.
Still looking through
You
these.
ever make a level in Godot and it kind of just looks like, so you want to just, but you can't? Oh, now you can, because we'll be talking about how we can use grid maps to create completely destructible environments. Let's take a look at what we're going to need here. We have a grid map set up with a bunch of blocks you can place around, and if you don't know how to do that, you should check out my grid map tutorial. Here, take a note of the size.
Dude, I'm doing this one. These other ones are probably great. I really want to focus on this one.
Of the tiles.
I've been really
And
wanting to
if we
do
look at our
voxel
tile set, each
stuff lately.
them
I've been
has a
like
static
fucking
body
watching videos
the
about
collision
talking about them and stuff.
and the size
some
of these
awesome
collision
ideas, I
shapes
think.
is the same as the size of the tiles. The other thing we have here is a character controller taken directly from my FPS tutorial series. The important part of this are the bullets, which can tell us the exact point where we hit the grid map. We have raycasts on them, and this raycast doesn't necessarily have to be on a bullet, it could just be on our character if we want to point and click
Shit, I
to
may just have
destroy
to
the
continue from the
tiles.
zombie
Taking
video,
a look
honestly.
at the code here, every time the process function fires off,
Good AI. Oops.
we check if the raycast is colliding. What we want to do here is track if we collided with our grid map by checking if the
Again, I feel like this guy is great. He's just way too quick about going through everything. At least with the last couple of videos I watched. He's just really hard to keep up with. But his stuff works most of the time, at least. Because I think we're on a slightly newer version, but still. Let's finish watching this. Not this, this.
Common issues you may run into is how to do two separate things at once, such as attacking while moving in a run and gun situation. As state machines are exclusive entities, one machine handling two different states doesn't really make sense, but you also don't want to have to duplicate every movement related state for every attacking related state so that you can have every possible permutation handled by one state machine alongside managing whatever data or animations go along with all of that. The solution sometimes is to just make a second state machine so that you can have one set of states for movement and another for attacking, though note that you will want your animations for the two states to be separate as well if applicable. This configuration is known as a concurrent state machine and is a solid choice when you have multiple states to manage that are largely or wholly independent from one another. To create one, you just make a second state machine using your implementation of choice and pipe each event from the parent to both state machines. If we were to extend the original starter state machine to have a concurrent state machine, the scene would look like this, and our player code would now pipe events to both state machines. The rest would be as before, with each state machine managing the states that they're responsible for. But what about if one state machine needs to know what the other is up to? Maybe you can only do a big attack when you're not in a jump state, for instance, but otherwise can do attacks as you please. Likewise, maybe you shouldn't be able to start jumping when a big attack is in progress. In cases like these, it may be enough to just give each state machine a reference to the other so that state checks can be ran where appropriate. But as much as we'd like to keep our states and potential concurrent state machines completely independent of each other, there are times where data needs to be shared between them beyond what a quick and dirty bit of code can solve. Maybe the run state should drain stamina, impacting how long future run states can be maintained. Maybe using any ability should prevent you from using another for some time. Or maybe you just need to remember the last time an event happened in some other state. Regardless of the specifics, it all comes down to the question of how to share data between states, and there are two approaches I tend to lean towards. The first is to lift data up the hierarchy. I mention this because it's important to remember that state machines are for state-independent logic, and shouldn't necessarily maintain every bit of data your character may have. Some items, such as character stamina or other stats, probably belong higher up the chain and should maybe be in their own component so that you can easily manage related features, such as adding status effects, displaying stats in the UI, and so on. You will have to do a bit of wiring to get the data available in the states where it's needed, but that's just how it is sometimes. Other times, having a data store that can be used by the states to read, write, and share data between can be an option. This could be something as simple as a dictionary on the managing state machine which the states can have a reference to, or even a separate component that can run any amount of custom logic, emit signals, and whatever else you need. Alternatively, if you don't want to have a shared data store, you can always modify your states and state machines to return and pass data around directly. A simple setup might involve returning an object when transitioning states that holds both the new state to transition to and any relevant data it may need to be aware of. As you can probably tell, you've got options depending on what you need and what appeals to you. It's all just tools in the toolbox, and what you'll need will vary based on your situation. And that's all I have to say about state machines for now. As a reminder, this is just a few techniques I think are useful to know and to get you thinking about how different problems can be solved. But there's plenty more that I've excluded for one reason or another. If you want more reading on state machines specifically for games, maybe check out Game Programming Patterns or Programming Game AI by Example.
Okay, so even though I was asleep through half of that, basically
and
asleep through
welcome.
half of that, I think I basically get the general
In the
premise.
last video,
Essentially, just make different points, point to other different points when you do the thing. Okay, I'm half kidding, but like, let's say USG script project, right? So open this up, right? And say scene, bam, scene, node. Right. Say, fuck you. B, C, D, F. So I understand this is your character, right? Actually, no. I'll say it, let me. call this node this. Do this, drop these into here. So this is essentially like movement A, movement B, movement C, movement D option. Say this is the jump state, this is the idle state, this is the movement state, this is the attacking state. And essentially what this does is it calls each of these, and they're all have their own scripts. They're like saying like do fucking the idle here, whatever the fuck. And it calls them, and when you say you're in the idle and you need to call this, it has an the ability to call to the like attacking function down here that has its own line about fucking punching or something. Winch. You get what I'm saying. Something like that. That's what I'm understanding, I think. And then when you're attacking thing, it doesn't really call it anything else, really. Well, just like midair stuff while you're jumping or staying still, stuff like that. That's why I think I understand. There's a way of like like not necessarily compressing it down, but like simplifying the way so you don't have a massive spaghetti code going on like I did with my project, which was not there. Let's see, this is just me bullshitting. Like this, for instance. As y'all remember, like if we go in here, look at this. Look at this hot garbage, this hot mess. All this stuff that depends on other things happening at this right time. And this one takes the direction. This checks. This one is friction depending on where the ocean there. This would be a great example of this for like and be like a part of the in-air function, or state machine thing. That'd be one of the states, this would be this would also be a part of the first part. This would be a part of the idle or moving function probably. Then move to the in-air function for the rest of the jumps. Now this is on floor, so this could be another the walking or standing still function. This was another in the air function. And there's another in the air function or state. Sorry, I keep saying function state. And these animations themselves could be parts of their own states. So it's just a way of like reversing it down so I don't have this massive fucking list of things to go through. That's how I understand it. Am I right about that? I think so. But that's what my understanding is, or comprehension of it is. I'm just gonna look at this. I like this woman's style already.
Hi everyone, and welcome to a brand new series
Hello,
where
lady.
we will look into how we can make a Bloxy voxel terrain in Godot. Terrains like this is something I keep coming back to and have experimented with both using WebGL, OpenGL and Godot, especially when I studied software engineering and computer science at uni.
One thing I want to state real quick. I know for a fact I don't have the qualifications to be doing this. But you know what? Fuck it. I want to look at this anyways.
So,
this is really fun.
This is something I've wanted to make a series on for a really long time. I'm currently using Godot 4.4 Beta 1, but I'll keep updating whenever a new version of Godot comes out.
Oh, here
My
we go.
main goal is to...
Oh, let's see if she held true. Oh, 4 weeks ago. I know about greedy meshing and also chunks. So, yeah. She seemed to have relatively kept up to date. I mean, nonetheless, she's still at it. It's not like she's uploading every day or anything, but she's still working on it and stuff. Nice. I think we're on 4.6 now. Something like that. But, yeah. Just want to look at this.
To guide you through all the ins and outs of what a world like this requires. We'll add and improve things in incremental steps. However, if you're more interested in just getting something to work and not a deeper understanding of it all, then I suggest you go search for a voxel plugin for Godot instead. During this series, we'll touch upon several interesting topics, including procedural generation, profiling and optimizing, comparing solutions, multi-threading, and much more. And now, let's get started. I've already created a new project using the Forward Plus renderer and created a 3D scene.
Specific renderers? I always saw that forward plus in the top right. I never knew what that meant. Let me look at this. Okay, mobile and compatibility. I said this is for porting, like, reasons. Like, this is so you can port your game to other, like, devices, like consoles or mobile phones. Stuff like that.
For the first naive approach to create a lot of blocks, we will be using the Godot CSG Box 3D node to create our blocks. So let's add one of these to our world and run the project to see what happens. Well, we can't really see anything here. And this is because we need to add a camera 3D and move it back a bit.
One thing I'll say, I'm glad she's kind of like doing this like from the ground up. Because like I was afraid that she's gonna get into some stuff that I had like no frame of reference for. So I knew that was gonna happen. And everything. So I'm happy she's not doing that. And she's actually like taking us like from the top, you know.
If you select the camera node,
Also, I read that CSG cubes would be terrible for voxels, but I think she's just doing this as an example thing.
you can also click the camera preview here to see what the camera is seeing without having to run the project.
Oh, I didn't even think
We
about
can
using
also add a
transform while you're
color
in
to
that
our cube
mode.
by adding a new standard material 3D to it and change the albedo color.
Yeah.
And finally, we can add a bit of lighting by adding a directional light 3D node to the scene and play around with the rotation of the light. And then I'm also quickly moving the camera a bit up and rotating it so we're looking at our first little cube from another angle, which makes it easier to see how the light affects the cube.
Oh yeah.
Okay, so now we have our first cube. But what we really want is a lot of cubes generated procedurally. So let's add a script to our root node and start by adding an exported variable that will define the size of our first little world. For this, I'm assuming that our blocks will have size 1 in all dimensions. So if the world is 16 by 16 by 16 large, we have 16 to the power of 3 positions where we can potentially place a block. I'm beginning with a very small world, and hopefully you will soon realize why. For this first little introduction, we'll just be placing blocks at random in the world, so it won't actually look like a terrain yet. We will come to that later. We want all the random cubes to be just like our first little cube, so I'm also adding a ready variable to store a reference to our default cube so we can duplicate it in a minute. To create our first
drag
little
that
world, we
code.
need a ready method. And here we'll be using 3 for loops to go through every single position we might place a block. Now we need a way to determine if we should place a block or not at a given position. For this we can use a random number generator, so let's create one in the beginning of the ready method. I've left a link in the description to where you can read more about the random number generator node in the Godot documentation. Okay, so for each position, we then create a random number using the randf method with no arguments. Using the method like this will return a floating point number between 0 and 1. Next we can check if our newly randomly generated number is larger than 0.5, and if this is the case, we create a new cube by duplicating the default cube, set its position, and add it as a child of the root node. And finally, at the end, I also remove the default cube from our scene. Now let's test and look at our first little random world.
Hell yeah.
To make it easier to test how this scales, I'm just quickly adding an exported variable for the cutoff for placing a cube. At this point, I encourage you to just experiment with the different values for both the cutoff and the size of the world. Why do Bloxy voxel games not just use this simplified?
I forgot she's using I just realized, yeah, she's using randf. Is that what that says? Where is it? Wait, what? Where is the... Yeah, randf. Yeah. That's random float. That's the reason she's using 0.5. I was thinking she was doing, like, if it's 1, it would be over 0.5. So instead of 1 and 0, you know? But it's a float value, not integer value.
Approach.
I see, that's a weird way of
What's
doing
the
it,
main
but alright.
problem here? And how does the size and the density of the world affect the time it takes to generate the terrain using this solution? If you want to test all of this with something that maybe looks a bit more like a terrain, you can also use the Godot Fast Noise Light node instead of the random number generator. And instead of using randf to get the random value, we can then use the getNoise3D instead and use the coordinates as the input. This will return a value between -1 and 1, so keep that in mind when you set the cutoff value. You can read more about Fast Noise Light in the Godot documentation.
What the fuck? I didn't know it had something like that.
And congratulations! Now you've created your first procedurally generated blocky voxel terrain. It might not be ready for a full-blown game yet, but it's a very good place to start. Next, we need to analyze the problems and lacking features to determine what to do next. I'm thinking that the biggest problem with the generation right now is that it's just too slow. So, one thing we could explore next would be how to move this into multiple threads. Another thing we need before we can try out more advanced solutions for generating and optimizing our terrain is a way to move the camera so we can explore the world better and also get a feeling of how the algorithms we use affect the frame rate when we move around. And finally, we need a way to measure how fast a solution is. So we need to look into how we can profile a solution so we can properly compare any future solutions we might try out. Which of these would you prefer to tackle first and why? Please let me know in the comments below. And in the next episode of this series, you'll see what I decided to tackle next. As always, the project files for this video are available for selected tiers on Patreon. Please remember to like, subscribe, hit the bell and all that if you want to see more like this in the future. Bye!
Hell yeah. I will like and subscribe.
One of the
That's
first
fucking awesome. That's good series. I like this woman. She has a good energy to her. So I had no idea that there was a fucking like a random terrain generation function thing. What the fuck was it called?
Games not just use this simplified
Fast noise light. That's a good plus. What? Noise using fastest light arrow, which is places several noise arrows, including cellular, Perlin value, and more. I know about Perlin noise. I've heard of that before. Frustrating noise values are in the ratio of -1 to 1, but not always. Some of the cellular noise algorithms return results above 1. No, my gosh. Sorry. Okay. Cool, we got Fractus. Really, this is. Well. Alright, sick. Well, I think that'll do it for me tonight. I'm sorry about today not being as energetic or what have you, or hell, I didn't even fucking do anything. But I guess I learned something. I know about this now. But yeah, I've just been tired today. I really want to stream. I'm sorry. I feel bad about not being able to stream lately much. But I have been. I only missed like a day or two, but I want to do this every day if I can help it, because this is like what I want to do. But it's just, I just need to work more, and it's just, it's causing issues. But we'll get things figured out. I'm sure I will. So that's also the reason why I'm tired a lot of times. I start up streams because I just, oh boy. Other than that though, that'll be it for me tonight, guys. I really want to actually work on like voxel stuff, even though this is way above my pay grade and everything. I know for a fact don't have what it takes to really make anything worthwhile. It's still something I'd really like to screw around with. I need to actually fill these state machines in like an actual like thing. I'm probably gonna do that in my own time. But do know I will be off tomorrow. I have a bit of a meeting I need to be a part of. And something I got to be home for because it starts at a certain time. I don't want to end up missing it because I'm out of the house. And it's just, stuff like that. But pretty important to me, so I'll be doing that. I'll stream shortly after because it's should be ending like a few hours before stream, I think. I don't remember exactly the time, but I'll be here. That's the main thing I'm trying to say. So, guys, yeah. Other than that, I guess that'll be it for me tonight, guys. So, I'll see you all again tomorrow. So, yeah. Good night, everybody. Bye. 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 Bye.